First of all, very quickly, who are Western Power Distribution? So we're the distribution network operator for South West, South Wales, East Midlands, West Midlands. We have 7.7 million connected customers, that's metered customers, including demand and generation, and over 55,500 square kilometres of service area. In the UK, there's obviously 6 different distribution network operators, 14 different licence areas. It's fair just to point out that obviously as a distribution network operator, we're not an energy supplier. So we take the electricity network from the GSP, from the national grid interface, right the way down to the electricity meter and not beyond. First of all, the network challenges presented by a transition to low carbon future, and the reason we're actually innovating and looking to do lots of the innovation techniques. Firstly, there's lots of uncertainty in what's going to occur, the scale of what will occur and the timing. So electric vehicles, heat pumps, different microgeneration, large-scale DG integration. When will it come, and at what scale and what time? And obviously the network needs to be ready and flexible for that time when it does come. And from the point of view, the reason we're innovating and looking for this is that we could actually go and look to build the grid a lot bigger and build it twice or 3 times as big. But obviously we're being incentivised to look for flexible innovation solutions, which means that actually we can add extra capacity to the network until such a time we actually know exactly what is the solution of the future, and then reinforce to that. So some of the uncertainties around the local generation, so solar PV, wind, CHP, energy from waste, and there again the demand, the electric vehicles, the heat pumps. One of the things that adds the uncertainty is obviously there's many different aspects that can influence the uptake, so feed-in tariff, renewable heat incentive, government schemes, which can have a dramatic effect as we've all already seen. And as has probably been said already today, that the networks weren't originally designed to accommodate the large amounts of small distributed generation and demand sources as they currently are. They were designed in a different era. So the innovations to look how we can take the existing network and try and innovate it in order to make it more flexible so it can cope with all of these. These 2 graphs are from our business plan. These are our anticipated uptake in PV installations and heat pumps. And it's fair to say that these are actually a lot more conservative than the DEC low estimate. But these have been based on a company who's done an assessment as the customers that are connected to our networks, where they are, what types of property they are, whether they're suitable for electric vehicles, heat pumps, solar PV. And from that, we're using this to try and estimate what the impact will be on our network. Very quickly about the innovation funding. Ofgem has made available several different streams of innovation funding to allow us to innovate. Firstly being the IFI, which is very much focused on research and development, so the TRL level 1 to 5, so from blue sky thinking up to one of a kind. They then brought in the Low Carbon Network Fund, which I won't go into a great amount of detail because we haven't got a lot of time, but it's available on Ofgem's website. 2 different tiers. Tier 1 for relatively smaller demonstrations that each distribution network operator can register projects over and innovate as long as it follows either a new technology, new commercial arrangement, or new operating procedure. And then Tier 2 being a larger funded amount of money that's competed against annually. So all the different distribution network operators put forward their project that they believe will make the biggest difference to GB. An expert panel selects which projects they believe should be funded. Western Power Distribution, like all distribution network operators, have an innovation fund. The primary reason for this is for us to research and develop and hone the techniques that we believe will enable us to run more flexible networks, to prove they work, and to bridge the transition from being a good idea to an aspect that we can adopt as a standard policy. So we can put it forwards into business as usual and offer this on a wide scale. So we take projects, we do one-offs. If it's needed, we then replicate it, and then we have the confidence that we can write a policy around it and offer it to you as an alternative to conventional network reinforcement. Our policy and our Future Networks programme is built around 3 main pillars. So networks, how can we demonstrate the improvement to networks? Customers, how can we work with and benefit customers? And finally, how can we improve the performance of the distribution network to all customers? A very quick overview of some of our projects, focusing very much on the ones that affect DG developers. we have a rather large-scale energy storage project that's been part funded through IFI, which is the first development of its type that I'll speak about later. It's a pumped heat energy storage system. It's 1.4 megawatts, 6 megawatt hours, and this is an 11 kV connected device that we connected at one of our primary substations. We have a series of Tier 1 projects. The LV Sensors Best Buy reports, it's already been said that the LV network is where we know least amount, and because the network is unmonitored, in areas we need to go back and retrofit it, but not everywhere. So we need to develop the techniques of how we can have the distant assets, and where we need to, we can quickly and cost effectively fit monitoring so that we know how that network operates. As has already been mentioned today, the connection of DG, as you're all aware, can influence voltage levels, particularly in rural, long, weak networks. We have a project that's been funded through Tier 1, which is a connection of some relatively small SVCs, static VAR compensators. The aim of those is to see how we can control network voltage on single feeders and also do it as a wider primary area to work with the on-load tap changes to give a steadier voltage level both during maximum demand, minimum generation, and during maximum generation, minimum demand. We have a project PV impact on suburban networks where we're monitoring areas of Nottingham, Asperley, Broxtowe and the Meadows to see what the impact of solar PV is on our networks. From these areas we've seen that actually the solar PV, whilst isn't reverse power flowing through these areas, is having a significant impact on the current harmonics, and actually the current waveform on these networks is no longer sinusoidal but instead triangle waveforms. And we're researching the effect of that and seeing where it's a big issue, so it's going to be more of an issue on rural networks and what we can do to ensure that it doesn't influence the quality of supply to all customers. Mark's already mentioned the early learning from the PV LV clusters and also the LV Network Templates project. The ones in dark green are our Tier 2 projects. They're more of our flagship projects looking at bigger, wider scales. We have Falcon, which is around our 11 kV network in Milton Keynes, which is looking at how we can assess how the network will need to be reinforced in the future. So we have a tool that can transform how the network will evolve and then look to see which techniques we should use in different locations in which order, both conventional and innovation as well. And the more innovation trials that happen, the more that gets added to it, the more data we have as to which trials and which techniques will be most applicable in the different areas. The Lincolnshire Low Carbon Hub we'll go into great detail on in the next slide. Solar Bristol, a small scale project based in Bristol, which is looking at how customers can get more benefit from their domestic PV and also from their INCs, so schools and offices. How they can use more of it themselves and how they can have less of an impact on the distribution network. We are retrofitting energy storage into these properties. In domestics, 4.8 kilowatt hours, in industrial and commercial properties, up to 19.2 kilowatt hours. We're also operating a DC network around these properties, which is transforming the lighting circuit, putting existing lighting over to very efficient DC power sources, allowing people to plug their DC power sources directly to this network, which means they don't have the efficiency lost from the AC back to DC when it comes from a DC generation source. It also means that we can remove all of the small, inefficient, noisy power converters that are often DC, which are designed down to the smallest penny, in order to put it on one central high-quality inverter, which can reduce the current harmonics on our network. Lincolnshire Low Carbon Hub, one of our Tier 2 projects. Lincolnshire is very rural and very adaptable for and has great conditions for a lot of DG, particularly wind and solar. And as such, a number of connections have been made over the years, and now new connections very often trigger large amounts of conventional network reinforcement, which traditionally means installing large amounts of cable back to early points on the network. And this can be prohibitively expensive, and we had a large number of connection inquiries that didn't proceed just because of the DNO point of connection costs. So we entered this in the Low Carbon Network Fund with 6 different techniques to see how new generation can connect and how we can change the distribution network to lessen the impact of DG. 6 main techniques, the first of which is dynamic line rating. Our overhead lines operate with fixed summer and winter asset ratings, and we're looking to see how we can actively calculate these ratings to fit more generation to that network during times when it is colder and when it's windier. Network enhancements. When we rebuild our circuits and rebuild our assets, we tend to replace them with the current policy. We're looking in this area as actually, can we build things ahead of need? And what should we put in? So if we're replacing an overhead line, what size conductor should it be? And what functionality should it have? So the overhead lines that are near the end of their life, we are putting in larger size conductors, and we're also fitting them so that they're suitable for optical fibre to be retrofitted to them to increase the enhanced communications that's required for a lot of smarter networks. Commercial arrangements I'll come on to next. We're fitting a large fax device, a STATCOM at 33 kV. It's a 3.75 MVAR unit, and this will be the first time it's been used in this way on a 33 kV network to absorb reactive power in order to reduce the effect of voltage rise during minimum load, maximum conditions, put at the weakest point on a network where it will have the maximum use. We're also doing dynamic voltage control. So, as we mentioned earlier, voltage rise is one of the limiting factors of DG connections. Our voltage controlled at Skegness for this entire primary network and around, and it's set as a one setting for 365 days a year, 24 hours a day. So we set it up pretty much for worst case, which is maximum generation, minimum demand with a set point, which means during those conditions, the network will all be within statutory limits with a certain bandwidth. Through this project, we will actively calculate what is the most appropriate voltage for this network here to be running at, so all of the points operate within statutory limits, which means during the summer months, typically when the solar PV is highest and we have minimum demand and we have generation supplying the local demand, we can actively lower the voltage at Skegness, increasing the headroom on the network. And finally, as already been said today around radial feeders, we're going to be creating a 33 kV active ring. So we're taking two radial feeders and we're connecting them through as a network ring, fitting enhanced protection systems, which means we have a more flexible network operation and power will flow through the least path resistance, reducing the impact of voltage rise. So these are the 6 techniques that we're doing in Lincolnshire to try and demonstrate how we can connect more distributed generation. Innovative commercial arrangements. The network is designed pessimistically as a passive fit and forget connection, which means we calculate maximum generation, all the generation on the network, all at maximum at the same time. It's credible, it can happen. At the same time, we have minimum demand. Equally, it's credible. We also have to calculate to make sure that the voltage wouldn't be within the maximum headroom, so we put the voltage at the maximum headroom it could be operating in, and take certain n-1 scenarios. All 4 of them happening together are plausible scenarios that could happen over the life of a generation connection, which means we have to design our network, because it's passive, to those areas. But because of all those things having to line up in time, it actually means that there is extra capacity in the network, which is available at times, just not every time. So we're looking to see how we can offer innovative commercial arrangements to distributed generations which aren't firm connections, which means that generation could be constrained during the small amounts of times. The sort of amounts we're talking here, so the next generation that hits in this area or connects to this area would be about 17 hours in a year. But those are 17 hours over that period that we would have to ensure that that generation was reducing its impact on the network. So voltage rise can happen during the maximum generation, minimum demand, and the high voltage levels. So during that time, a distributed generator can change its power factor, which can reduce their impact on voltage rise, and something we'd look to offer as part of a connection agreement. And if that hasn't been effective, actively reduce the output during that time until the demand or other generation reduces their output to allow it to be absorbed in the network area. And equally with thermal constraints, the same aspect of reducing the generation demand whilst it can't be absorbed locally and can't flow through the network. So we're considering developing a last-in, first-off scheme which will give a generation the knowledge of where they are in the stack, what level of constraints they're estimated to see, and we're also developing a software tool which is taking all of our network data, So we can present it to people and show them, and they can use it as a tool that will be available online. So they can plug in their generation onto this tool and see the impact that generation is having on the network, and allow this to estimate the level of constraints that would happen with that innovative connection to allow people to come to us and explore this alongside a conventional network reinforcement. So people can decide whether conventional or an innovative connection is the most appropriate for them and their generation. Moving on to energy storage. The main aspect of the Low Carbon Network Fund is to innovate. So it's to allow us to develop the tools so we know which techniques we should be using when they're most appropriate, when they can be quicker than traditional network reinforcement, when they can be cheaper than traditional network reinforcement. But one of the principal fundings of LCNF is that not everything will be smart. There will still need to be conventional network design and conventional network reinforcement. We can increase the capacity through LV Network Templates project, through different design, operation and techniques, so design and also operating of different networks as it comes on, so that we can ensure that that network is best designed for those areas. And then there's all the other different low carbon network fund type techniques that the other DNOs and ourselves are developing and trying to hone and trying to bring into business as usual. We're not sure where the scale will be. We can't at this stage confirm exactly which techniques will be best in which different area. But through the LCNF projects, the IFI projects, and the projects that we do as ourselves anyway, we're trying to determine exactly what the benefits are and where it's the right place to do it. I focus very much on Western Power Distribution projects. However, there's a number of different DNOs. There's 5 other DNOs, all with their own innovation portfolio, all very much looking to see as to what they believe the future innovation should be for the network. Being that Low Carbon Network Fund is customers' money and it's funded through customers, it means all of the learning is publicly available. So as part of our project, we encourage and we have to disseminate our information not only to our other DNO members, but also to the wider public. So everything that we learn and the trials that we're doing, we record rigorously the documentation of the learning that comes from it, so we can hand that over to the other DNOs so they can use it and apply it. So anything that we can show as being the right thing to do, hopefully they'll also pick up and adopt it as business as usual. Energy storage, the future of energy and keeping the lights on is one of the aspects. Although you'll see at the moment that actually energy storage sits at the moment at the top of our triangle, so the smallest peak. One of the reasons for this is currently energy storage is very expensive. And although a number of distribution network operators are doing trials into energy storage and the different technologies, there will be a changing of the technologies. And it's the same in the IT industry, where you see that actually costs come down remarkably quickly. And a lot of us at the moment are demonstrating energy storage as a technique to learn how we could use energy storage, not fully believing that the current technology will be the one that actually makes it as the business as usual, but so we can learn how storage can be used, who it should be owned for, when it should be used, so when that technology does become available, then it will be used more extensively. So the idea of energy storage first will make its way in very niche applications, and then hopefully as it becomes more established and more cost effective in more areas. The reasons we're very interested in energy storage is this is our predicted annual load growth based on the customers we have on our networks, what demand and what generation we think they will be connecting to their network, or to our network and to their properties, and also the energy efficiency, which will reduce demand. And as you can see, it's going up quite considerably. From that point of view, it won't actually go up as a maximum demand. Some of it will go up as peak demands. And at the moment, our traditional conventional network is designed for the network peak. And obviously one of the advantages of storage is that it can be used to peak lot, to take that peak and to transfer it to another different area. One of the key challenges with energy storage is who should own it and where should it be. And that's one of the key things that we're looking to determine from the Low Carbon Network Fund trials and the IFI projects that we're doing and the other DNOs are doing, and something that we are all working together through an energy storage operators forum so that we can share the lessons that we are learning to try and develop a UK guide in order to determine how storage should be procured, installed, commissioned, and owned and operated. One of the things I'd like to draw your attention to, which comes back to the smart techniques and actually the ability for our network to connect demand. One of the limiting factors of generation connections is because there isn't enough local demand at minimum demand times to absorb that generation. And obviously if that does increase and the minimum demand increases over time, that will increase the ability for our networks to absorb increasing levels of generation. So energy storage, where does it sit on the network? Truly, everywhere. So we're looking at 3 different particular energy storage projects in different locations. The first one being the large project I spoke of earlier. It's a 1.5 megawatt 11 kV connected synchronous motor generator connected to a pump that stores energy as heat in thermal vessels. It can then be switched back round and can operate the other way and act as a generator. A very novel, different type of energy storage which uses a lot cheaper raw materials. And this is very much at the lower TRL level, but a storage technology that we think may well develop in the future to be one that we can use. This is being installed at 11 kV at our primary 11 kV bars. And obviously the advantage then is on the 11 kV bars, on the primary substation, and all the way back up through the network. So that's where the advantage of that storage could be used. And one of the things we're very much looking at, and other DNOs are looking, is to where should storage be located? Should it be in our substations? Should it be out on the network? Should it be paired with a generator? One of the reasons for that being is a DNO's use of storage is actually quite small. We design around the maximum demand, the worst periods, so typically on an average network, and there's no such thing as an average network, you maybe think about 30 days in a year is when a distribution network operator really needs storage. During that time, there's many different benefits that could be had from it. So it could operate in the store market, it could be used with intermittent generation, it could be used to lessen the connection for a generation so that you could absorb more generation during the peak outputs and then put it out during the minimum generation periods. And from the point of view of one of the things that we're looking for energy storage is who should own it and where are the different revenue streams which can make storage more financially acceptable and allow storage to become a normal technique and being sort of installed and rolled out across the network at a quicker rate. Another project we have is our Falcon, which is part of our Tier 2 project. One of the techniques is to look at energy storage. This is a lithium-based energy storage that comes from GE. And this is 5 different energy storage, 50 kA, 100 kilowatt hours, which will be installed in distribution substations and will be installed at the LV bars. Obviously the advantage of that, of moving down, is there's then the benefit on the distribution transformer, the 11 kV network, and if rolled out across a wide enough area, all the way back up through as an aggregated power source. And obviously then these storage devices can start to be used as a virtual power plant. You can group them together across feeders, across primaries, across grid groups to start having small amounts of storage as large amounts of variable demand and generation. And then finally we have our Solar Bristol project, which is actually beyond the electricity meter. It's in people's homes, which is actually beyond where we normally operate. And Ofgem have permitted this as part of the Low Carbon Network Fund. Not that we see ourselves as owning and operating energy storage in customers' homes, but rather because we're trying to demonstrate the principle and the value and how it could work so we can then disseminate this, share it with the wider market and allow other people to bring up and take on the technology and roll it out. The key aspect we're looking from this is what's the value to a DNO? So how can we use energy storage to reduce the voltage rise on an LV feeder by customers storing more of their local generation for use when they want it? How can they also reduce the impact on the distribution network during the peak time, so the middle of winter when there's very little generation? So how can they charge their batteries off peak and use them during the peak times to reduce the impact on the network? And what's the value stream for a distribution network operator? And then how could we use that to fund that to help make storage in people's properties more cost effective? The other aspect with trialling through this project is a variable energy tariff. So we're looking to the future to see how storage can be used as a tariff aspect to try and incentivise people to use more off-peak electricity and less peak electricity, not through them necessarily having to change their behaviour, but through technology and intelligent technology that will be optimised to lower their impact on the distribution network. At this time as well, we've talked about 3 different energy storage techniques, and also people also link into that to demand-side management as a storage technique of moving demand around. And people often, it's quite evocative when you say of people controlling their LV load. One of the things I'd like to point you to is electric heating and radio teleswitching. Doing demand-side management is being pitched as a smart technique, but actually it's been done for years. And we have, and suppliers have, control of people's electric heating so it can be operated during the night times so that it can reduce the impact during the peak times, and customers have cheaper energy for when they need it as a heat source. And the energy storage doesn't actually just need to be batteries. It could also be a storage technique, hot water heating. People taking their solar PV and using it as a storage mechanism as hot water, and using it as hot water. And these are a number of the different things us and other DNOs are actively researching to see is what is the most appropriate storage technique in the different areas, and how can we use these as a smarter technique to reinforce the distribution network, and how can the benefits be shared across all of the different market. Thank you very much.